Kentucky in computer science ever since. He and I, of course, have written many papers together, and I introduce him with great pleasure.
Too late. So, Professor Artemov is, as you heard, in three places: philosophy, mathematics, but also computer science. This will be computer science talk, okay?
Feel that dog, I heard it say.
So here is it. When I started as a logician, and did many things actually in logic for many years, I didn't dream that logic will become a practical, practical computational tool. That was not what we saw when we started. Many people who are here in this room started when logic appeared to be extremely esoteric. That's not what it is today. And I am going to talk about this actually on some aspects of logic which provided foundations for practical systems, which actually derive all sorts of applications, including actually computers, which we are all using here. So I will be talking about solvers. And so let's see what those things are. I will be talking about that. I will focus on three things, but actually I suspect that I'll be able to cover only first two of those: SAT solvers and their applications, answer set solvers, which is related to logic or here and there, and then also SMT solvers, SAT solvers as management tools. So what are solvers? Well, solvers actually are you have some kind of formalism. It can be Boolean logic. It can be something else, as we are going to see today actually with answer set programming. And you have a solver for F is a computer program that does the following: accept as an input set of constraints in that formalism F. I'm sorry, what's written there, and returns one or more solutions to these constraints, given enough of resources. Maybe it will work forever. Maybe it will be working, till the end of time, okay, or of our time. What constitutes a solution depends on the formalism. Okay, so I will discuss these two types of solvers, but also a little bit more of those things. All right, and so the message which I will place right now at the very beginning, so who knows whether we would have time for the message at the end, is the following: logic, just unlike what was happening 40 years ago when we all were listening to beautiful things about infinitary things in logic and things like that, it became a practical, I want to stress the word practical, computational formalism. There are many logic-based formalisms that are used in applications. I will be talking about two, but there are actually many others, okay? And I would like to stress that logic, and certainly Gödel saw it clearly, is quite often just a syntactic sugar for description of computational mechanisms. Okay, so we think about this in terms of logic, with formulas, models, and things like that. But in reality, there is a process of computation behind it. Okay, this process of computation is usually encoded in various issues related to the syntax, its processing, actually, and proof theory. Okay, so we are going to see this a little bit. And I will be talking about some formalism, actually propositional logic and something called stable semantics for logic programs. But there are many others. And some of those are developed by people who are here in this room, and in particular Professor Artemov. Okay? And there are new systems are constantly invented, and they are useful. And so we are going to see this. Okay, so first thing I will be talking about something called SAT. SAT is it's propositional logic, depending, and it was studied for depending how you count. 160 years, if you are a mathematician, you think about Boole, and if you have a misfortune to be a philosopher, 90 years it's Wittgenstein or similar people. Okay, so but really what's important are the applications to electrical engineering since the work of Shannon in the late 30s of 20th century. Okay? In particular, in principle, circuits such as those that are running our computing devices can be described using Boolean functions, and therefore propositional logic. Okay? By SAT, we mean a language that is a collection of strings consisting of propositional formulas that possess satisfying assignment. Often one limits to the class of formulas, for instance, to CNFs, DNFs, 3CNFs, and so on, so on. Okay? More often than not, we want to find a solution that is a satisfying assignment, not only establish its existence. Okay? That's what we would like to see. We have some kind of, so imagine that you have a circuit, okay, and you would like to know, will this circuit ever produce 1? Yes, so that's what you would like to see. You have some inputs, you would like to know. Well, it looks like pretty trivial question. We'll see that it's actually not a trivial question at all. So there is a simple way to do this. You just simply you enumerate all the assignments and then just simply compute the value of input formula on those assignments one by one. Well, when there is, say, 256 variables, maybe you won't be able to do this till the end of our time. Okay, that's what it is. Okay, so this trivial algorithm would be exponential. Its running time would be exponential. The number of variables, certainly serious problem. So let's deal with CNFs. There are many other techniques for encoding Boolean functions and those things which are inside of computers. Okay, so there was this. So let's deal with the CNF. The proof theoretic approach pioneered by Quine was to close the input CNF. Which is a set of clauses under something called the resolution rule. Okay? You can think about this as some kind of a computational process. All right? And Quine proved that the CNF formula phi is satisfiable if and only if the closure of phi under resolution does not contain. So it looked like it has nothing to do with anything computational and so on, but David and Putnam found that the closure can be done piecemeal by eliminating variables one by one. And if the empty clause is not computed, then a satisfying assignment can be computed from those deltas, those things that you process in this. So if you have luck, actually, and the whole thing doesn't grow to exponential size, it will be pretty fast, actually. And it's one of those techniques which is used for simplification. The first crucial improvement was due to Davis and Putnam. Closure under resolution is very expensive. It is not so if you close under limited form of resolution, where you allow only for derivation when one of the inputs is a literal. There is a unit clause. Okay? And then it was transformed by David, Loveland, and Logman that instead of just this variable elimination, that actually you can transform into backtracking search. Okay, so what do? You are taking partial assignment, that is assignment only to some variables in the formula, and then you organize this into something called dynamic search tree. And so what happens is that as long as if you didn't succeed in satisfying your formula yet, actually then you choose a variable and you take extend your assignment by putting here 0 or 1, and that's you do the backtracking search on this one. The process that I described as of the unit resolution, actually closure under unit resolution, is a computer science lingo is called Boolean constraint propagation. Okay, and given enough of time in this search process, well, either you find a contradiction or you find a solution. Okay, so that's essentially what it is. In the meanwhile, actually, in the 70s, Cook has shown how to encode fixed horizon runs of non-deterministic Turing machines by means of CNFs. Okay, there is nothing particularly deep in this theorem, but it has to be proved. Okay, so such runs can be encoded as CNFs in polynomial time in the size of the Turing machine. The effect of this one was that there is a class of problems, which we called NP, which has this property that there are polynomial time reductions from such languages to CNF. So what does it mean? It means that if somebody gave you the machine, some device which solves CNFs, you will be able to solve NP problems. Well, it's actually a stronger property because it's not only on the question of existence of solution, but solution themselves. Okay? So if we have such a program, right? I mean, the question now is if there are such programs. And of course, here is, I mean, in that type of situations, you want to give examples. Okay, so you have your Sudoku from your local newspapers. You are frustrated. It has 6 stars. You encode this thing, the fact that the value k is in the cell ij as a Boolean variable pij, k write 27 constraints on rows, columns, and squares. 3,916 constraints to make sure that no cell contains 2 values. Then add the units provided by your local newspaper, submit it, and then in the morning you come to your office, show to your coworker and say, you see, here is a solution. I solved it. Okay, so here is what it is. What I want to mention is that this first part of this can be pre-computed, that we can describe the problem, and then we have the instance which corresponds to your daily Sudoku in the newspaper, right? Okay. So this is actually a little bit more. You must have heard that there are these Japanese people who, long beards, whatever, they make Sudoku by hand. Of course it doesn't happen. They use computers to design Sudoku and heuristic function to establish their hardness, actually. And so that's what happens, okay? Not only Sudokus can be solved by such solvers, they can be also designed by such solvers, okay? And that's what happens if you just simply go to my site, you will get this daily, you can get whatever is diagonal Sudoku, you name it. But really, such solvers have different uses, and so the question is, how can we use such solvers for practical problems, okay? One of the most important applications of such solver right now is something called combinational equivalence checking, or EC. You have 2 combinational circuits, that is the circuits without memory, okay, without flip-flops in them, and you just simply would like to ask, well, are those actually equivalent circuits? There is a good reason for this, because all, and I mean all, well, maybe not all, but 95% of the circuits used in our computers are produced in the offshore foundries. Okay, and how do you know that they didn't put there something which will send immediately your all data actually through the internet to the archipelago Tonga? Okay, well, certainly it could happen. Okay, so and when they design this input, design this circuit, then they actually produce this thing. It will not be exactly what you told them to do. They will put some simplifications. How do you know that this stuff and that stuff are actually equivalent? What do you do? Well, you take one circuit, which they designed, and your circuit, which is maybe described in your favorite language for description of such circuit. You take a mitre of these 2 circuits, that is the Boolean sum of those things, and hope that it has no solution. Well, unfortunately, you would say, well, this problem must be extremely difficult. It is co-NP complete. Well, however, those things are actually done out of common specifications, so in principle you should be able to find. And I will not describe the details for this one, but actually the point of all this is that this is an important application, that this application really happens, and that for the leading tools such as ABC out of UC Berkeley, underneath of this thing, there is a such solver which tells you actually which actually is an engine which is used for computation. Meaning what? This means that what we thought, and some of us at least thought that it's completely trivial, when they taught us logic, propositional logic, and so on, so on. It's not trivial. It has most important applications. Okay, and so just as I am talking about about those things where you can use these things, well, you can use it, for instance, for planning. An example of such thing is SATplan, which is essentially a planning software using SAT solver as back engine. You remember that I was talking about that SAT solver is being used underneath some computer program. Yes, and so there are other things. So computer engineering is a major consumer of SAT. Say you want to implement large finite automaton, you would like to ask, well, am I getting into an unsafe state? Will my automaton run forever? Will my automaton be stuck in some state? Yes, so all those things are those questions they are asking when they design it, right? And so we need to be able to answer this. And so what happens, it's no surprise that the impetus for improvements of SAT came from computer engineering community. The first major improvement implemented is a system called GRASP out of the University of Michigan. Was actually proof theoretic in its nature. When we backtrack, in reality we compute another clause which is another clause which is a consequence of this theory, because you made choices. It brought you to the contradiction. What does it mean? That the conjunction of these choices is false. That means disjunction of negation of these choices is implied by your theory, right? Well, so that's partial closure under resolution. Quine would be happy. Okay? Well, so that's what it is. The name of the guys who invented this is Marcus Silva, and who was a student of Sakala, found such clauses. They can be simplified. The shorter the clause, the better, better to add it to your theory, right? Because maybe in some other part of the search tree you will be able to get to the contradiction faster. Well, so what happened is that they coined it as a graph theoretic construction. In reality, it's proof theoretic. Okay, so what happens is this made graph for some time fastest solver, but there were more. There are several reasons why the BCP is applied. Clauses are simplified, new units are found, contradiction, that means backtracks, are computed. Significant improvement was watched literals technique, which means is the following. If you have at least two literals in a clause which have non-assigned values, certainly this clause will not be simplified to a unit, right? So for that reason, essentially you don't have to consider it until you have to. Okay, so you just watch these two literals until one of them is assigned, then you have to get back and do something about this. Whereas discovered by Stickel and Zhang, and then improved by Malik and Princeton electrical engineering in his Z-Chaff solver, this led to further gains in SAT solving. Remember, these circuits which are here are large. This Moore law and things like that says that the circuits get only larger. Okay, and we certainly have to deal with the larger circuits, and we have to solve these equivalence checking problems, for instance, for that type of things. So I want to tell you that actually there are other techniques for representing these circuits. Okay, that is formulas of propositional logic. There are, for instance, reduced ordered binary decision diagrams by Bryant, Boolean polynomials by Zegalkin, and things like that. Both are inefficient, but very attractive, because they are canonical. You have many circuits which will describe your favorite Boolean function, but when you order have a fixed ordering of variables, then both of these techniques give you a canonical representation. Well, so in particular, ROBDD are popular in the electrical and computer engineering for a variety of reasons, actually, because ROBDD not only tells you whether there is a solution. It tells you can compute all solutions if there are. And there are very attractive algorithms. So I want to mention this that you will know about this. So, and again, if you need to deal with this decision diagrams, there is a tool called CAD out of Colorado. Then you have solvers. I mean, I will mention that there are a couple of names here, like Franco in Cincinnati on his SBSAT, actually non-closal solver, and so on and so on. There are many solvers, actually. Here is, again, a couple of names, Minisat, Picosat, March, and others in common use. Currently, actually, one of the best is called Cube and Conquer, but you need to know that those things are applied and are used actually daily when people change the design of because you have to realize that the design of chips is changed daily. Okay, they will find another bug and they will have to change something. Okay, and then they have to check, and so they use these things constantly. So, computer science is something which is completely balkanized. What happens is the following. You have a principal conference of a small community, okay? And then then there is a group of people, maybe smaller, maybe bigger, who are around that thing, okay? And so they may be, in this particular case, in case of SAT, they also have now their competitions. And the competitions will be dealing with practical problems coming from industry, random problems, and things like that. And so they also have their own online journal called Journal of SAT. You can find it there. And SAT papers are published in other conferences such as AAAI, ICHCAI, and so on and so on. So what I tried to do until now was to convince you that the solvers exist, okay? But SAT solvers is not a unique formalism actually to do solving. And I will be talking in another formalism which is a little bit closer to my heart because I contributed to it. And there is a couple of people here in this room who contributed to this significantly. So let's talk about this one, answer set programming. Roots are in generalization of Horn logic, initially grounded in knowledge representation formally such as default logic and circumscription, but also logic programming and database theory contributed. Prehistory is the following. You have the Horn clauses. Everyone knows what Horn clauses is, and those are of two types. It has at least at most one positive literal, and it can have many literals. So one of those is a kind which we call it program clauses. It means you proved Q1, Qn, you are now a proof of P, and the other one is constraint, which tells you that you cannot have together Q1 and Qn. Okay? Theories consisting of program clauses have a list model. The model is described by the set of atoms evaluated as true in this case. These models are list fixed point of suitably defined monotone operators. Okay? And so a Horn theory has a model if and only if the program part actually satisfies the constraints. The history of this whole thing is that at a certain moment, Horn logic, allowing for variables and function symbols, was actually became a theoretical basis of a programming language called Prolog, which was an object of a minor cult and of significant hype, okay, which actually resulted that the very nice ideas were actually, well, things were done, but actually it was overhyped, as everything in computer science, which is moderately attractive, it becomes overhyped, okay, for some time. All right, so the reason why it was successful was the following. The Lis-Herbrand model of a finite Horn program, variables, function symbols are allowed, is searchable using backward chaining. That was actually known to Kling. Okay, and everything, quite a lot of all these things were known to our masters. Okay, so it so happens that under suitable coding schemes, the list model of such program is recursively enumerable. Okay, backward chaining, you just simply go backward chaining through this one using some kind of a search formalism, and you just be able sometimes to establish that something is in the model of in this list model. This led Kolmerauer and collaborators, based on the work of logician Kowalski, to implement that type of things actually and build a programming environment around it. However, in that process, they introduced useful but not clearly defined programming construct, which was called negation. Namely, you are not able to prove something. If you are not able to prove something, you accept maybe something else. It was completely unclear what does it mean. It was immediate and very easy examples can be given that this is not a classical negation. There is some kind of epistemic negation. Okay? Immense effort. I mean, you just simply go to those conference proceedings. All sorts of effort was spent into understanding what it could be. PhD were written. Grants were obtained. Tenure were obtained in various places. Mostly nothing came out of this. I mean, it's a very common phenomenon that what we do quite often is wasted. But that's the way it is. Okay? So anyway, no longer list model exists of this thing. So it was unclear what to do with it. To get things even more complex, another community, completely different from the first one, was involved, namely database community, because they also write horn clauses and things like that, implemented actually in the computer database program DB2. So what happened was that horn logic with variables allows to specify recursion, but the point of this one is that so why were database people interested? Because you can specify notions like a transitive closure, reachability in graph, and whatever you are able to actually reduce to this one can be expressed by such programs. So database community talks about data log when they write horn programs. Okay, because except that they don't. It became quite clear that you cannot use function symbol, and the reason for this is that you could do whatever you want, but the answers to database queries have to be finite because they have to be shown to you, right? So there must have been some limitations, and we'll see what those limitations were. When with this trouble or with negation, there were all sorts of things. There was a supported semantics, inflationary semantics, essentially invented by Moscovatis, and yes, actually, that's exactly what happens. Other programs, other proposals, and so on and so on. So essentially, they were wondering what would happen actually. You are dealing with inductive definitions that certainly program without negations do. What happens further? Well, maybe they said, maybe if we just simply limit the programs that you can write, everything will be just fine. Okay, so they introduced the notion of stratified programs, which were discovered by logicians Blair and also with a gentleman named Walker. Okay, and they rediscovered this because by a pure accident, Pfefferman and other logicians knew about such iterative inductive definitions for years. Okay, so Abt and Blair immediately found they knew how to write programs that with negation you can define all sets in arithmetic hierarchy. This is a very bad news because try to actually do something, compute something, in sets which are not necessarily RE, right? So that created serious problems. But in 1988, Gelfand and Lifshitz proposed a different semantics called stable model semantics of programs. This same semantic was actually proposed. It was not clear that that's the same semantic by Bidouin and Fruadevo. So our clauses now look like this, all right? Programs and sets of such clauses. And here is the description of the process which leads to the stable model. I am not going, these slides will be available publicly. If you are interested in see how stable models are computed, you just simply get it, okay, from the conference site or from, I will gladly provide it for you. But anyway, there was a process. This process involves guess, okay? So I will just simply, the time, I have a limited time to do this, but let me tell you that, for instance, for Hamiltonian cycle, and maybe I will tell you, we can write this type of things. You can describe the problem of Hamiltonian cycle in that formalism without any problem. And so I want to tell you that you certainly can do this. And here is, you just simply describe the general problem of Hamiltonicity, and then you add the instance, okay, and then you solve it. Phenomenon is actually very easy to write. It turned out, proved by Professor Remel and myself, that all search problems in the class F and P can be solved this way. Okay, so essentially, it turned out that you can this schematic description of your problem, and then you get the description of the instance and submit it to ASP solvers. That makes these things pretty attractive, actually, because you just simply work on the level of the problem itself and just simply shove the instance into a general program which allows you to solve. There are other areas, and I won't enter into this one. Well, what applications? I want to tell you that essentially your favorite graph problems, vertex cover, independent set, kernel, you name it, can be solved in this way. Okay, and so the point of this one is that to some extent is an exercise in knowledge representation. You describe your problem, then you add the instance and send it to the solver. So the question now is, are there solvers? Yes. Well, and it also looks like we are talking semantics. Right? Because I was talking about stable models, right? Well, so the point of this one is that in reality, even though we are talking about the models and things like that, what was discovered by Nirod, Remel, and myself is that really it's a proof theoretic situation, and in fact the proof techniques which are there are similar to unit resolution, but with some interesting twists. Okay, and we looked at this one. Well, here is what we used, but again, in the interest of time, I would rather skip the technicalities, okay? So what happens is that when you have this structures, you remember that I told you that you have a formalism, then you have things which are of interest for that formalism. In this case are those stable models of Gelfand and Lifshitz. Okay, they are all minimal, they form an anti-chain. If the program is stratified, then it possesses unique stable models, and that's exactly the same thing that Abt and Blair and Walker proposed. So it was obvious very soon after the proposal of the thing that this is the thing, that this is the correct semantics. Okay. So what happens is once you have, I mentioned that you can define all arithmetic sets by means of suitably chosen stable models. Well, actually, much stronger property holds, as shown by Nirod, Remel, and myself. Stable models allow, in some precise sense, and I don't want to enter exactly what it means, but up to degree preserving one-to-one correspondence, effective closed subsets of Baire space. Okay, so the collections of, so what it is that here you have the effective closed sets, here you have a program, and there is a one-to-one degree preserving correspondence between the elements of this effective sets and the collection of stable models. This last result, and the strengthening, allowed Sensor and ML, who actually analyzed these things very precisely from the point of view of recursion theory, to get a number of powerful results on the index sets of properties of such programs. So the point of this one is that there is this practical aspect, which we'll see some solvers. I will be discussing solvers. And in addition to this, there is a deep mathematics which is behind these things, very similar actually to SAT, if you will. So again, if we are talking about finite propositional programs, the basic complexity issue is how complex is to find a finite proportional program possesses a stable model. The problem is NP-complete. Okay? When people realize that type of thing, a new area of this solving was invented. It's called answer set programming. It maybe started, like, I would say, around a little bit, maybe like 10, 12 years ago. Okay? So the point of this one is that the solvers for ASP, I told you that you can represent many things in ASP. Well, if you can represent it, the question is, can you solve it? That is essentially, you describe your problem, submit it to the solver, solutions are coming back at you, given enough of resources. Well, so many solvers were implemented over the years. The names will be dropped in slides which follow, okay? And then there were extensions. You know, you have things like you allow for aggregate atoms, such as cardinality constraints of the form not less than k but no more than L atoms from X are true, and so on, so on. Okay, weight atoms, choice atoms, and semantics for this were proposed and implemented. And again, in the whole thing, I described how you deal with the Hamiltonian cycle and how you deal with the graph coloring. If you are interested, actually, you can see it in the slides. There are solvers, I told you. Here are let me drop a couple of names for leading solvers. S models out of Aalto University in Finland. C models out of the University of Texas, Austin. CLASP, the leading solver right now out of the University of Potsdam in Germany, and DLV out of Calabria and Technical University of Vienna. Okay? If you just simply see this, look at this, well, you have actually two possibilities at least, if not more. One of those, well, actually more. The ASP solver may be native, that is essentially you solve it without looking to any other formalism, or you can reduce it to another formalism. For instance, using SAT solver as the back engine. Actually, this was tried and succeeded using something called loop formulas and things of the sort. Was actually quite an interesting area of research. The leading solver right now is a CLASP, or to be precise, something called Potasco, which is a complex of solvers associated with this is out of the University of Potsdam. Okay? Interesting thing was that eventually they found that the same techniques of search techniques that were used in SAT solver with modification can be used for ASP solvers. And so that's pretty hot area right now. Okay? So aggregate atoms were pioneered by S models, a little bit a wider class of programs than called disjunctive programs is done by DLV system, which is also very strong on their connection with database, but that's another matter maybe. Like SAT, there is an ASP community. They have they are organized around conferences in originally something called LPNMR, Logic Programming and Non-Monotonic Reasoning, but that's what it is. Because of logic programming roots is also associated with ICLP, since logic programming is slowly dying, actually hype goes away. Many related to knowledge representation, because you know how to write it. It makes a lot of difference how you write it, okay? The point is that if you write it well, it will be solved faster. These issues are important. You know, in mathematics, we are not necessarily interested in effectiveness, right? But here we have to, okay? So again, there are SAT competitions, a site called Asparagus, and whatever is it. And I want to mention that that type of things are in use, okay? So there is a couple of current research topics. Well, essentially, what are the constructs? I mean, how do we program in those things? In SAT, you essentially it's a brutal form. You write what you need to write, transform it from some language, and then submit it to the solver. That's what makes SAT powerful. Here, you are really interested also not only in solving it, but we also are interested in how you write your program. So there is this current research by Deneker, Liller, and Rosinski on construct use in ASP. Okay? The problem with this one is that unlike SAT, ASP is not compositional. Adding new clauses does not necessarily produce a set of stable models. Drastic things happen there. For instance, compactness fails, as shown by Remel and myself. So what could be done to make ASP at least a little bit more compositional? Quite a lot of research is there. And then something truly unexpected happened. It turned out that this ASP sync, which I told you, ASP sync, which is I told you is related to logic, logic programming. It turns out to be its closest relative is something which is a logic, which is sometimes called Gödel-Smetanic logic, sometimes logic coherent. There is an extension of intuitionistic logic complete with respect to the two Kripke models with two clusters. Okay, that's very, very strange situation. And it turned out that various important issues there, for instance, when you can substitute one program for another in arbitrary program, are related to this logic. Who would expect that anything like this could show up in practice, right? Well, so certainly that's a very, very strange situation, and I think quite a lot of this research is still being done. So I told you that there are other solvers. So here are others, so let me, in the rest of this presentation, there are other solvers. For instance, maybe you express your property as a QBS, quantified Boolean formula, and want to solve it. Quite attractive from the point of view of electrical engineering, okay? Then there is the following kind of a meta situation in which you use the SAT solvers as management tool to manage constraints written in decidable fragments of predicate calculus and possibly its generalization. So here is what happens. Maybe you have a theory, open theory in Pressburger arithmetic. You represent it in the clausal form, and then use SAT solver. You have a couple of atoms. You can use the Pressburger solver to solve it, but to manage the entire thing, use SAT solver. Okay. Well, there are other situations where you have that type of management. Management in other things. So, in addition, so again, it's not clear what will happen in ASP, but some attempts were done there as well. So, just on the, it's 45 minutes right now. I thought that only Professor Remel can fit 45 slides into 45 minutes, but maybe we succeeded in this one. Here is the message, final message to take home. SAT and ASP are areas where much happens right now. Both are based on well understood mathematical foundations. Okay, so there is a serious mathematical work which came into the mathematical foundations of this entire thing. Okay, both are well supported by reasonable solvers. Okay, unlike SAT, ASP was always concerned and still concerned with knowledge representation and principled programming. Okay. There are solvers for other formalities within widely understood what we call constraint satisfaction. Okay? And these are also actively researched right now. Okay. Well, thank you very much for your attention.
So again, questions from the audience? Yes?
7 years back, I was at a small meeting in which the slogan, there was a lot of discussion for the slogan that compositional calculus plays a role in computer science that linear algebra plays a role in. The same role that linear algebra plays in applied mathematics. The position was that instead of finding ad hoc ways or, using special methods for specific problems, the scheduling problem, for example, that we discussed. You would just translate this into SAT, and then there's this other community that tries to find better and better SAT problems. It seems like some of the things you mentioned, particularly involving these ASP solvers, as some of them being based on SAT solvers, is relevant. Do you have any comments on this? I don't know what has happened.
Well, that's exactly what happens. That's exactly what I was saying. There is no difference of opinion between you and I. What happens is this. You translate it to SAT, you translate it to other formalism and whatever is it, which is supported by solvers. If you have something of this sort, the solvers given enough of resources and a good encoding will give you a solution. That would be a phenomenal thing, and especially in computer applications.
Having said that, one thing that's different is ASP is a much friendlier way to program. It's much easier to do knowledge representation. There's a whole series of extensions that you can do, and SAS is, still translating into SAS solvers. The final output for into SAS solvers is over. So that's one of the advantages.
More questions from the audience? Otherwise, of course, I will add in a remark, which is never a question. There is this business of being able to translate these problems into integer linear programming. Those packages work extremely rapidly. That was pioneered by my student Jaroslaw, who died at an early age in the 1980s, so it hasn't been pursued to the extent to which it might be. At that time, it was fair to say that if you take these problems, these same problems, and put them into the latest integer programming package, that they ran competitively with all the systems available at that time of the sort that he's been describing. And the underlying thing there is that the theory of integer linear programming is basically the theory of the additive theory of real numbers with the notion of integer additive, which is a logic connection. So there are other things here too. There are a lot of different electronic things. Do we have any other questions?
Maybe a small remark of historical nature. This negation of failure problem, which you mentioned, I remember that I was working in a very novel area, which is called probability logic. Solve bolus, we had probability operator, and of course we did a lot of progress, exciting area connection to the second Gödel completeness theorem. Wonderful things, a lot of papers, as you said, PhDs and tenure positions. But then at that moment, I was also under a strong belief that this is the theory of probability from the capital letter. And then this simple problem came, just negation is failure. Something is not probable, just deal with it. And I tried to deal with it, and I realized that the probability logic is not enough. We have to be constructive. We have to be efficient. And then it was one of the first hits to my strong belief that the probability logic is the answer. And we end up with, very shortly after, we end up with logical truths. And that's the whole new view of the whole thing. So it was very constructive, very instrumental, this program. Thank you.
So apropos of Anil's comment, how much impact has geometry had on ASP and more generally SAT and so on?
Well, that's a completely missing area, which you're suggesting, which is very good.
I would say the following: the connections to this is not the only talk which will be devoted here to ASP, and I think that at a risk that maybe I am misrepresenting it, I think that the question of geometric considerations and generally question of what kind of spaces we are dealing in, generalizations at least of ASP, will be discussed by Professor Remmel on Friday. Okay.
Any further questions? Okay, it's now time for talk.